ไม่เคยทำเลยตามบอกคนลงมาเลยอุ้ยนี่จะเดินกันเราก็ตอบคำถามไม่กลับเราต้องโดนตอบด้วยเลยช่วยบอกไปว่าก็ไปหาคำอ๋อไปร้านเราทำได้เราทำได้จริงๆคุยรู้เกรงใจเลยอยากไปด้วยเพราะว่าพี่ไปซื้ออยู่ก็จะเราอยากใช้แล้วก็หวานนี่คือแบบว่าที่ทำแล้วก็คือ
Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Good afternoon, everyone who actually watching online and actually in this room. And welcome to IF Colloquium number 35. Correct. Okay, I think it's correct. Okay. So today's speaker is Chakraborty. Correct? Is that right? Okay. So he's now is a postdoc, right, at Department of Physics, Chakraborty University. So he's going to give a talk about almost L CDM models and then called dark energy. Please give welcome to Saikat from China. He's Thai. Okay. Please.
Yeah, my Thai name is Saikat Chakraborty.
Yeah. I just learned that.
Well, thank you very much, Humphrey, for the invitation, and it's always I'm always happy to be back at IF. So this is a work that basically I started back when I was a postdoc here at IF, but yeah, it came out very recently, and by the time I have joined Chula already. So what I'll talk about is, what I'll talk about is this is a pointer.
Yes, there's a pointer. And
Yeah. What I'll talk about is, as you can see in the title, almost Λ CDM cosmological models and how dynamical dark energy can be achieved in those models. And this is a work that I have done with some of my collaborators back in South Africa. Okay, so there is a plethora of dark energy models that have been introduced to explain the late time acceleration of the universe, and proper theoretical tools are necessary in order to classify these dark energy models. They are usually called diagnostics. There are two such frequently used diagnostics in the literature. There is one kinematic diagnostic that is based on something called cosmographic parameters. And it's called state finder diagnostic. And there's a dynamical diagnostic that is done WW prime analysis of dark energy models. So these parts I have bold-faced because I will elaborate on these parts in the following slides. The state finder diagnostic, the kinematic one, basically classifies the dynamical dark energy models in a plane defined by these two quantities. The first is related to the second derivative of the scale factor of the universe. It's called deceleration parameter. The next is related to the third derivative of the scale factor, which is called the jerk parameter of the universe. Properly normalized to make them dimensionless, of course. And sometimes in the state finder diagnostic, I will say most of the time it is customary to use these two quantities instead. One is the jerk parameter and one is, they say, state finder S parameter, which is a combination of the jerk and deceleration parameter. On the contrary, WW prime analysis classifies dark energy models in the plane W, which is W dark energy, equation of state parameter of the dark energy, and W prime, which is the derivative of the equation of state parameter of the dark energy with respect to logarithm of the scale factor, sometimes also called Hubble time. The motivation of this work is to properly address the correspondence between these two diagnostics. Let me first come to the WW prime analysis, and this analysis has been put forward first by Caldwell and Linder in a seminal physical review letters paper, and later on there has been many works, but yeah, these are some of the works I found really helpful. One by Scherer and one by Takeshi Chiba. So I just show the screenshots of some of the papers. What is the basic argument behind this diagnostic or this analysis? So the equation of state parameter of the dark energy is a fundamental physical quantity that characterizes the dynamics of the dark energy. And the dynamics is, in a dynamical dark energy, you always have a W prime. So a dynamical dark energy model can be characterized by some kind of a flow in the W prime plane. And the basis of the analysis is that it is possible to set some kind of upper or lower, or sometimes both, limits on W prime corresponding to each dark energy models. So these limits usually come from physics analysis, for example, the form of the potential, the nature of the scalar fields, which is like whether it is canonical or non-canonical, and that some speed should not go superluminal, that kind of requirements, put the limits. The Lambda CDM model corresponds to the single point -1, 0 in the WW prime plane. All other dynamical dark energy models occupy specific regions in the WW prime plane, thus giving show some examples. The first one is taken from the Caldwell and Linder TRL paper. So what Caldwell and Linder did, they analyzed quintessence model, very popular dark energy model with canonical scalar fields, and they classified quintessence model into, they showed that it is possible in WW prime plane to classify the quintessence model in two classes, which they call freezing in and thawing out. What's freezing in? Freezing in is our models where earlier the equation of state of dark energy was greater than -1, but then it freezes to the value -1 as time goes on, and the thawing out model is like earlier the equation of state of dark energy was -1, and then it evolves away from -1 towards values higher than -1. And as you can see, these two models can be classified, and there it is possible to put limits on the value of W prime, and they occupy distinct distinct region in the WW prime plane. So from the observational data, if you can somehow plot W prime versus W for some range of redshift, and you see that which part of the WW prime plane it falls in, so you can distinguish between the two models. Subsequently, this kind of analysis was extended to other models as well. So this is a figure I took from the Chiba paper. So what Chiba did, Chiba considered some different models, like something called tracker quintessence model. And for tracker quintessence model, W, the equation of state is always greater than -1. So it's always on this part of the plane, and based on some earlier bounds, Chiba could get this kind of a lower bound, the uppermost curve. So Chiba could only get the lower bound for the tracker quintessence models. But Chiba also redid the analysis for phantom, and for phantom, he could get both upper and lower model, the lower bounds, which occupy this region of the phase space, the shaded region. They are for phantom dark energy models whose equation of state is lower than -1. So this is the kind of discriminatory power that WW prime analysis have. Now let's come to the state finder diagnostic, but before going to the state finder diagnostic, I have to introduce cosmographic parameters. Cosmography is the model-independent study of the kinematics, just the kinematics of an expanding universe. and in terms of Taylor coefficients of some kind of a measurable distance, for example, luminosity distance or angular diameter distance. And the parameters are like Hubble, deceleration, jar, snap. There is an infinite hierarchy of them. I just showed the first four. They are related to successive derivatives of the scale factor of the universe. Now, it can be shown that any cosmological model in general relativity can be kinematically specified by an algebraic constraint. For example, if you take the general Λ CDM model, including the global spatial curvature, so you do not assume a spatially flat universe, you can show that the evolution of the universe in this model satisfies this kind of an algebraic relation between the cosmographic parameters involving deceleration, jar, and snap. In particular, if you go to spatially flat Λ CDM model, it becomes jar equals to 1, very simple, and this has been used a lot in the literature. This is something Humphrey will also talk about how we down the line, I think. Okay, now let's come to the state finder diagnostic, and this diagnostic was introduced by Varun Sahani, Tarundip Saini, Starobinsky, Ujjaini, Alam, and later on, of course, many people have worked on it. What was the basic arguments behind they're introducing the state finder diagnostic? They said that for dark energy models, where dark energy is not actually a perfect fluid, which is basically most of the dark energy models, because they have either field theoretic origin, like canonical or non-canonical field, or a modified gravity origin. The equation of state parameters for this kind of model is not actually a fundamental property. Strictly speaking, what you do is you write down the FLRW field equation, homogeneous isotropic field equation, then separate out the Einstein tensor part on the left hand side, take everything else on the right hand side, and separate out the pressureless matter part, and whatever remains, you say, okay, this is my an effective fluid. That works in the homogeneous and isotropic diagram. But if you go to a different diagram, for example, say part of FLW diagram, then equation of parameter actually loses its sense, because in a part of FLW diagram, the parted fluid is not a perfect fluid anymore. There are off-diagonal terms in the pressure tensor. And also the propagation velocity is of small inhomogeneities is not like CSS squared equals to dp0 dp0. It's not like that. So in that parted level 1 has a parted equation of state, something like that. So they argued that instead of like equation of state, if we can make a diagnostic based on kinematic quantities, for example h dot, basically derivatives of the scale factor or Hubble parameter, this is free from such ambiguities, because these are independent of the model, where the model is scalar field or a modified gravity. This is independent of the model. So that was their argument. And how is it used to distinguish between different models? So in the state finder plane, whether you define it as S, and okay, I took this two figures from the paper of Starobinsky and Sahani, and they use that terminology R, but this R is basically the same as the cosmographic Jark parameter J. So this is not a new parameter, but it's just J. In the state finder plane, different models occupy different, not occupy different region, but corresponds to different families of curves. For example, in the state finder plane QJ, Lambda CDM model is a straight curve at the center, and then something called Chakraborty gas models of dark energy. They correspond to a family of curves that looks like this. Quintessence corresponds to some other family of curves. And similarly, if you go to the state finder plane SJ, Lambda CDM is just a point, and different other curves, different other models, they give rise to different families of curves. That's how you distinguish them in the state finder. Okay, so now we have seen that in the WW prime analysis, Lambda CDM model is specified by W equals to -1, W prime equals to 0. On the state finder plane, is is defined by the cosmographic condition Jark parameter equals to 1. Let us try to elaborate on these conditions a little more. So see, if you take the Lambda CDM model and write the cosmological field equations for the spatially flat Lambda CDM model, you get these two equations, well-known equations. Rho is the energy density of non-relativistic matter, and rho p subscript dark dE is the corresponding quantities of dark energy. Now, using the above equations, you can obtain the dark energy equation of state, which is a pressure over energy density, which comes out to be like this. Then, if you use some cosmographic relation, basically the scalar curvature can be expressed in terms of Hubble and deceleration parameter like this. If you use that, as well as a definition of the density omega m, which is the density abundance parameter, you can write the expression for W dark energy in terms of deceleration and density abundance parameter totally. Now, matter density abundance obeys that dynamical equation as I showed on the slide. This tau is basically logarithmic time again. Now, if you now impose a W dark energy equals to -1 into the expression of W dark energy, you get this equation, and if you now take derivative of this equation, this is a cosmographic relation that relates deceleration and Jark parameter. But you get J equals to 1. Very good. So W dark energy equals to -1 gives you J equals to -1. Sorry, J equals to 1. This condition, J equals to 1, kinematically specify the spatially flat Lambda CDM model, or better said, specifies the kinematics of the spatially flat Lambda CDM model. If we had introduced global spatial curvature, this would have been a bit different. There would have been the curvature abundance parameter added on the right hand side. But now, if we start from J equals to 1, it can be shown from the Friedman Friedman equations that you can write J, the Jark parameter, in terms of deceleration parameter and equation of state of dark energy and its derivatives in the following way. To get at this equation, you just take derivatives of the right order equation here. So as you can see, if you now set j equals to 1, it gives you the following relation, generic relation. W dark energy equals to -1 constant, which is the lambda CDM model, is definitely a solution of this equation. But this is not the only possible solution. It has a generic solution. The generic solution, if you solve this equation, differential equation, it gives you something like this. So the lambda CDM model is not the only possibility in the j equals to 1. It has a more generic possibilities. That's one nuance about state finder diagnostic. But what is this model? Basically, if you try to think physically and you solve the continuity equation, you get how the energy density corresponding to this fluid evolves. You see that one part of the fluid evolves as 1/a cubed, whereas the other part is a constant. So basically, this constant part, this gives you the dark energy, something like a cosmological constant. But this other part, this fluid also have another part, which is like behaves like pressureless matter, which tells like pressureless matter. So in a sense, this is like a unified dark fluid model. It describes a dark matter-like scenario in the early universe, and in the late time, it asymptotically approaches a cosmological constant. And P of dark energy, P of this fluid, the pressure of this fluid is constant because see rho of dark energy is proportional to 1 over W dark energy. This is called unified dark fluid model. If you see now, if you put in the general expression of W dark energy, if you put W dark energy 0 at 0 equals to -1, if you set it, then you see that the entire, like if you set its value to be -1 at present, its value is pinned down to -1 for all redshift. This is what can be seen from the expression. And also, if you see in the earlier slide that if you set W dark energy at 0 at present to be -1, there's the part that behaves like pressureless matter that is vanishing. So all the part behaves like cosmological constant, so you go back to the lambda CDM model. But in general, this is not the case. Now, if you go back to this expression of W dark energy and set W dark energy at present to be -1 here, this gives you a relation between the present day value of the density abundance parameter and the deceleration parameter, which is actually a known relation for lambda CDM model. So this relation, that omega m naught close to 2/3 1 plus q naught, this actually holds only for lambda CDM model, but it is possible to have other dark energy models which are cosmographically exactly the same as the lambda CDM model, but the relation is something different. The question now that we ask is the robustness. Even if I set things up in such a way that an exact lambda CDM-like cosmic evolution, like J jar parameter equals to 1, corresponds to an exact lambda CDM model. So basically, if I set, given that I set this condition that W dark energy at 0 equals to -1, which means W dark energy and all Z equals to -1. So I said exact lambda CDM like cosmic evolution is equal to exact lambda CDM model. Then does an almost lambda CDM like cosmic evolution, which is Jack is not exactly equals to 1, but almost equals to 1. Does it imply an almost lambda CDM model? Because see, you never from data sets, if you apply Gaussian processes, etc., and reconstruct the value of an expression for J as a function of Z, you never get exactly 1. You get 1 plus something times Z, something times Z square, like correction terms. So you always get an almost lambda CDM like cosmic evolution, but does it mean almost lambda CDM model? This is what we are trying to investigate, and it can be reframed. The question can be reframed as: does the kinematical proximity to lambda CDM model translate to dynamical closeness to lambda CDM model? The answer, as I will show you, is non-affirmative. And we have investigated this question using 2 explicit examples. If you take J equals to 1, Jack parameter equals to 1, and integrate it backwards, because it is related to third derivative of the scale factor or second derivative of the Hubble parameter. If you integrate it backwards, you get the evolution of the Hubble parameter as something like this, or in terms of scale factor, you get an evolution of the scale factor as something like this. Because of that, we took 2 prototypes of almost lambda CDM models. One is we took the evolution of the scale factor, and instead of 2/3 at the numerator at the exponent, we made it 2/3 times 1 plus epsilon. And in the model 2, we took the evolution of the Hubble parameter, and instead of like 3 here, we made it something like 3 plus minus 2 different exponents. Basically, if you calculate the corresponding cosmographic conditions from these 2 models, it comes out to be like this. The first one is J equals to 1 plus 3 epsilon 1 plus q. The second one is J equals to 1 plus epsilon. Actually, for the second one, we started from J equals to 1 plus epsilon and integrated backward to get this. But anyway, you see, if you take epsilon equals to 0, all these models, evolutionary models, go back to lambda CDM-like evolution. So epsilon is like a deviation parameter. Then based on this, we calculated all the necessary quantities like Hubble parameter, deceleration jar, density abundance parameter, and the dark energy equation of state. For the model 1, we can calculate all these quantities. Of course, integration is involved, so there are integration constants. But all these integration constants, there are 2 such integration constants, as well as that deviation parameter epsilon. If you calculate all these quantities today, it can be related to the quantities Q naught, J naught, and omega n naught, the present day value of deceleration jar parameter and the density abundance parameter. Why we calculated the constants in terms of the present day values of these quantities? Because these values you can constrain from data sets. This is for model 1, and when after you do this, after you evaluate these constants in terms of the present day values of parameters and substitute it back, I get some ugly expressions, but okay, this is still manageable numerically. I do the same for model 2. So we have everything in terms of Q naught, J naught, omega N naught. Now, if I substitute their values, I can plot them and compare how they compare with the exact Λ CDM-like evolution or exact Λ CDM model. But first, I need some values of Q naught, J naught, and omega N naught. So, by the way, if you calculate the present day values of W dark energy and its derivative with respect to the redshift, for example, this present day value, it comes out to be same for both the models. The expression in terms of J naught, Q naught, and omega N naught comes out to be same for both of the models. To plot now, I need some values of Q naught and J naught. So we try to see in the literature if there has been works on like model independent estimates of the present day value of deceleration and jerk parameter. And we found that it is possible to give model independent estimates of these quantities like, without assuming any particular underlying model, just from the data using Gaussian process, etc. It is possible to give bounds or best fit values to these quantities. And the best fit values I have written here, which I got from a paper, which is Q naught and J naught equals to minus 0.647 and 1.035. That paper is from, I think, 2023 or something. It may change a bit after recent observations. But anyway, we work with this one for the time being. And at first, let us choose, because omega N naught cannot be determined in a model independent way. Omega N naught is a model dependent quantity. It's the you can constrain its value only after assuming a particular model, a particular dark energy model, or at least a dark energy equation of state parameterization. At first, so we have chosen for the time being omega N naught equals to 2/3 1 plus Q naught. Why? Because we notice that this makes W dark energy at the present to be -1 for both the evolutionary models. So basically, whatever is the underlying model corresponding to those almost Λ CDM-like time evolution, they correspond to the Λ CDM, they coincide with the Λ CDM model today. Although they can deviate from Λ CDM model at higher redshift, today they coincide. There is the motivation behind taking is to just show that even if you set them to match today, they can still deviate at higher redshifts, but you need not necessarily work with this imposition. And I will show later on that you can better impose it from data directly. But again, data is model dependent. Omega N naught data at least. But based on that, you can choose the values of the deviation parameter, and they come out to be in the order of 10 to the -2 for both the models. Now, get to the interesting part. When you plot the kinematical quantities, for example, Hubble parameter and deceleration parameter for the exact Λ CDM model, which is the yellow curve, and the almost Λ CDM model, which is the blue curve, you see they are very close. But when you go to a dynamical quantity, for example, the equation of state parameter of the dark energy, you see that, okay, I have set them to be such that at z equals to 0, they coincide. I have said that for easy comparison, but you see that they deviate from lambda CDM model pretty fast, I mean pretty significantly. So even if they almost always remain close to lambda CDM model as far as kinematics is concerned, as far as actual dynamics is concerned, they grow very different to the lambda CDM model. And you can also see the same if you plot other model-dependent quantities. For example, the density abundance parameter for pressureless matter and dark energy. You see near z equals to 0, they are almost the same, but as you go further, they start deviating. For model 1, the deviation is a bit bigger than for model 2. The fact that they generically correspond, all those almost lambda CDM models generically correspond to almost lambda CDM evolutionary model, generically correspond to dynamical dark energy models, which are quite different from the lambda CDM model, is very apparent if you plot them in the WW prime plane. See if they were like close to if the dynamics was close to the lambda CDM model, I would have expected W dot energy prime to be something closer to 0 always. So basically, I would have expected a much flatter curve, but no, it's actually a pretty significant curvature there, pretty significant slope. What's the implication then? So again, by imposing omega m naught equals to 2/3 q naught, 2/3 1 plus q naught, we have set things up in such a way that the exact lambda CDM-like evolution corresponds to exact lambda CDM model as well. Now, one would have naively expected the small deviation from lambda CDM-like evolution correspond to small deviation in lambda CDM model, i.e. that means small deviation of W dark energy from -1. But what we notice is that even though the kinematic quantities like Hubble distribution, Jark parameter, or luminosity distance, I have included the plot of luminosity distance, they show small deviations. Model dependent quantities like energy density, density abundance parameter, or dark energy equation of state, importantly, they show pretty significant deviation. So the kinematic closeness to lambda CDM model does not necessarily guarantee the dynamical closeness to lambda CDM model. Even though a cosmological model may appear very close to the lambda CDM model, according to model independent kinetic data, like the luminosity distance redshift data, the model itself can be quite different from the lambda CDM model. If you put it in another way, even though the lambda CDM model may offer a very good fit with various sets of data, one cannot use this fact to confidently state that the underlying model is actually lambda CDM or something very close to it. Now it turns out that almost lambda CDM-like evolutions rather corresponds to almost unified dark field model, and that can be apparent if you follow the behavior of the dark energy equation of state over a larger redshift range. For example, this is what I have done here. I have followed the dark energy equation of state over a larger range. See, this is the lowest curve is the lambda CDM model, which is W equals to -1. And these three curves, red, green, and purple, they are that unified dark fluid model with various values of the parameters. So you see these values for these other parts, W dark energy today is not -1. So if it's -1 today, then it pings down the value at all z to be -1. If it's something different, it's a completely different model. Now my almost lambda CDM cards, they have a shape pretty similar to those of the dark fluid unified dark fluid models. What does it say? That if you consider all the possibilities of the cosmography admitted by the cosmographic condition J equals to 1, W dark energy equals to 1, which is the lambda CDM model, is not a very robust one among those possibilities. If you slightly deviate from J equals to 1, your model gets drastically different from lambda CDM. And given that Jz equals charge energy equals to 1 is not an exact but only an approximated condition as obtained from, say, luminosity distance versus redshift data, a unified dark fluid model in that sense is far more likely and robust theoretical option for a model if you calculate it, if you want to take into consideration kinematic data sets. But then now DESI, the dark energy spectroscopy instrumentation, lately has been talk of the town, and it makes sense to confront our models to some extent with DESI. What does DESI collaboration do? So DESI collaboration assumes the dark energy equation of state has a form like this: W naught plus W suffix A into 1 minus A. Or if you write it in terms of Z, WA times Z over 1 plus Z. So once you give a form to the equation of state parameter of the dark energy, is no more is model independent. Okay, based on this model, you can definitely constrain the present day values of omega m, the density awareness parameter, and W naught and WA once you specify the model. And this W naught and WA, by the way, can be related to the present day value of the dark energy, as you can see here, and also its derivative with respect to Z redshift evaluated at Z equals to 0. DESI collaboration paper gives only the first three columns, omega m, omega naught, omega a. They do not say anything about Q naught, J naught, etc. But from this, and using that earlier relation about relating W dark energy prime with Q naught, J naught, we can basically calculate the values of Q naught, J naught, and from that the values of epsilon, the deviation parameter that characterizes the deviation from exact lambda CDM-like evolution. And as you can see, the values of epsilon are actually quite large. For the first evolutionary model is 10 to the minus 1. Remember that earlier we took it to be 10 to the minus 2. And for the model 2, it's even worse. It gets to the order of like 1. This is a hint that basic collaboration probably implies a cosmic evolution that is quite different from the lambda CDM-like evolution. So it's quite different, it might actually be quite different from j equals to 1. Although I should mention that there has been criticisms of the DESI results as well, because some people say, why are you like some people say DESI's bounds or measurements are biased by a prior choice of these kinds of equation of state. And it is possible. But anyway, we have taken what is available and what most people cite. But then we have taken two data sets. The first is DESI plus Pantheon and DESI plus CMB plus Pantheon. So these two, DESI plus Pantheon and DESI plus CMB plus Pantheon. And then, based on the values of epsilon, the deviation parameter, if you now calculate Hubble parameter, deceleration parameter, you find that for the evolutionary model, almost equivalent to CDM model 1, the quantities, the kinematical quantities are quite, reasonably, I should say, reasonably close to lambda CDM, but for if you take the for any model, for both the models, if you take the DESI plus Pantheon data and the respective values, the evolution of the kinematic quantities are reasonably close to the exact lambda CDM-like evolution. But if you include CMB data in your picture, then it gets really bad. It's very, very, very far. Even the cosmography is very far from lambda CDM, and the same behavior persists for model 2. And this may have something to do with the fact that for DESI plus Pantheon, the deviation parameter epsilon is still less than 1, of the order of 10 to the minus 1. It's can still be considered a small parameter, so to say, but if you include CMB, for the model 2, it's larger than 1, but for model 1, well, it's 0.5, but anyway, we are getting what we are getting. Maybe we need to check once more. If we calculate the dark energy equation of state now, then we see some kind of a difference. So this is the exact lambda CDM model, which is flat line W equals to minus 1. And for the almost lambda CDM model with the DESI plus CMB plus Pantheon, is going into the phantom region quite quick at a redshift even below z equals to half. But if you take only the DESI plus Pantheon, it is still going to the phantom regime, but at a much higher redshift. And this curve, although it looks like this, if you extend it to higher and higher z, will go into the phantom regime. So DESI shows a non-phantom to phantom crossing in the course along the course of the cosmological evolution, and that is exactly what we are getting in the almost lambda CDM evolutionary models that we have considered, as long as we choose our constants in accordance with the DESI data. Now let me conclude the takeaway points. The takeaway points from these studies are these. So the cosmographic condition JARC equals to 1 is degenerate between lambda CDM model and unified dark fluid model. In fact, JARC equals to 1 corresponds to the lambda CDM model dark in WDE equals to -1 only if you impose the WDE at today is -1. That condition, imposing that condition, pins down its value to -1 at all times. But in general, it is not -1. Even if an exact lambda CDM-like cosmic evolution corresponds precisely to a lambda CDM model, that even if we set things up such that J equals to 1 corresponds to WDE equals to -1, mainly we impose this condition, there's no guarantee that this setting will survive small astrophysical uncertainty. So if you have Jz approximately equals to -1, that does not mean WDE is approximately equals to 1. If you have Jz approximately equals to 1, does not mean you will have WDE approximately equals to -1. The ramifications in cosmological model building is that since observational data usually gives J equals or almost equals to 1, at least before DESI, but never exactly J equals to 1. So a unified dark field model would be far more likely based on that kind of data. But then again, if we believe in DESI data and even after all its like criticisms, etc., if it comes out to be true, then we should say that it seems to point towards a cosmography that can be very different from J equals to 1. I couldn't find at least one paper that does a model-independent cosmographic study after the recent DESI data release that supports the fact that J of Z is quite very different from 1. Of course, this requires a new model building. And for any model building in dark energy, in the field of dark energy, the kinematic state finder diagnostic and the dynamical WW time analysis are two very popular diagnostic tools. But the non-robustness of the correspondence between these two diagnostics is something to be careful about. So if you see two models are very close in the state finder plane, that does not mean that physically they are also close. They can be very different models with completely different evolution for the dark energy equation state. Okay, thank you.
Okay, the question?
If we take the cosmic background cosmographic, if we take the cosmic background evolution with the supernova data, can we put a positive on a higher order negative positive vector like for other activity, for the time activities, then we will have it for channel.
Fourth order,
Yeah.
I mean, in principle, we can, but in practice, I have seen people constraining only up to like higher order, and that may have something to do with like when if you go to higher and higher order, the sensitivity of required from the observation is higher. So, which may be one of the reasons it is hard to constrain. So up to J, which contains like hard order of the scale factor, hard order derivative of the scale factor. Yes, that I have seen. But
Yeah.
snap, I have not seen that much.
Awesome. Because I just think that to distinguish between the exact lambda CDM like evolution and exact lambda CDM evolution and lambda CDM like evolution, I think we should go to the snap. Otherwise, because okay, we set j equal to 1, and then we try to, and then you try to compute the lambda CM like evolution like, and I think to confirm that this evolution is the exact lambda CM evolution or not, we have to go to higher other derivative, I think. Do you think about this?
I mean, see, when you, that exact lambda CDM like evolution corresponding to J equals to 1, that is a very much like theoretical construct, but if you actually get it from data, they reconstruct it as like, so what they do is they assume J equals to J naught plus J1 times Z plus J2 times Z square, something, and then plug it into their code or something which has the inputs from data sets, and then they fix, then they find the best fit value of J naught, J1, J2. So, I mean, you never actually get J equals to 1. You can get the value of J naught to be very close to 1. The best fit value is like 0.9 something.
Yes. But my question is, if you start from J equal to 1 and perform the integration, I mean the analytic integration, you get the some expression of Hubble parameter, right?
Yes.
And then for and of course you have the integration constant, right?
Yes.
If we choose the different integration constant, you get the something. You get the solution that you call the lambda CDM-like evolution.
From
right?
Starting from J equals to 1?
Yes.
No. Starting from J equals to 1, that is exact lambda CDM-like.
Oh, okay.
But for almost lambda CDM-like, you have to integrate from a condition that deviates from J equals to 1. So like J equals to 1 plus epsilon, or J equals to 1 plus epsilon times some function of Q. So like if you imagine the state finder plane that is spanned by Q horizontal and J vertical, the J equals to 1 is a line at the center. And different other models, theoretically, they are like curve in the JQ plane. For example, Chaplain gas models has some kind of curves.
Okay.
Quintessence has some other types of curves.
Okay, thank you.
Okay. For me, I'm out of the field, so it would be very not into depth question.
Yeah,
so actually, what are the observations made by DESI and whatever sort of thing that you presented here? Do they measure really the WDE
No, I mean, as far as I understand observations, I don't understand that much, but from the basic that what I understand, observations never directly measure equation of state of dark energy or the uh, like omega m, the density abundance parameter. Observations do not directly measure them. What they measure is some kind of distance, like luminosity distance, for example. So what they do is this luminosity distance, you can expand it in terms of redshift, where the Taylor coefficients are basically that cosmographic parameters. There is no dark energy equation of state or anything there. But then how do DESI collaboration, I mean that paper that they released, in that they have assumed a particular equation of state parameterization for dark energy, which is almost the same as assuming a particular model. When you assume a particular model and then plug it into your code, etc., then you can constrain the free parameters in that model, and that W naught, WA, they are like free parameters in the model, omega m naught, they are free parameters. Then they can measure it. They can constrain it. Yeah.
I see. I see. So I was wondering that basically in that data here, okay, they assume the WA, right? WA. So it means that they assume. I'm not sure if they assume or if it that it is the data fact that the WDE is evolved. I mean, for the exact lambda CDM model, you say that it's constant, right? Equal to the -1. So is this really from the data, or they need to assume that they need to evolve like linearly, or maybe evolve with set with some function of set that they propose?
Yeah, basically that's what they have done in the paper, that they have they are saying that, okay, let me assume that it's linear, okay. And then since it's linear, I have W naught and WA. If it was like flat, then WA is 0. But suppose it's linear,
Okay.
then what are the like best fit values of W naught, WA? But then if you
So we don't know for sure that the word behave in that way, right?
no, and there I can say that there has been some papers by important guys saying that the results that we get, the ones that I showed in the table, are subject to the statistical bias for choosing, that linear equation of state that you said.
Yeah.
What if I like? Can we not do it in a model independent way?
Okay. Another question. I know that set is related to the redshift. So set 0 is the present day, and set increases by the distance. Yeah. When we observe the past. I mean, from your model, or maybe in general model for that, they explain can be described as the function with respect to the parameter set here. Especially in your model, is it true if the set is negative? I mean, maybe you can predict the future of the universe.
Oh, but there's no data available from.
Sorry.
There's no data available from.
Yeah. I know, but I mean, I am talking about in the sense of predictability.
Oh, I see. Predictability. Yeah, probably. Like you can see what are the future attractors
Yeah.
of these models.
it's possible to see.
Yeah.
I haven't.
So that would be a problem if you thinking of that way, because of your data from the DESI, you assume the function would have one set over one minus set.
Yeah.
Or one plus set. I'm
They-
not sure.
They are
It's have like a pole in the future.
Yeah, they are specifically for Z.
Yeah.
Positive.
Okay. I see.
They make it for Z positive.
I see.
Any more question or anything else? So if no, then let's thank speaker. Yeah. Okay. And stay tuned for the next colloquium. Thank you very much for today. Bye. China. Yeah. I just learned his name today. This is China. Not Saikat. It's like you know what?
Thank you.